Hi, and welcome to the final video of our Tropical Jets and Disturbances sequence. In this video, we take a look at our final feature of African meteorology, specifically the Saharan air layer, a hot, dry, and dusty air mass associated with summertime sensible heating over the Sahara Desert. So as we jump in, let's take a look at this visible or true color satellite image here from late August 2019, where we have Tropical Cyclone Dorian here near to the Lesser Antilles to the south and east of Puerto Rico. And we see two areas, one to the southeast of Dorian along the northern coast of South America, and in particular this one here over the eastern tropical and subtropical Atlantic just off of the coast of Africa here. These milky brown tan colored regions are areas of dust particulates trapped in the atmosphere, and in particular this one here off of the coast of Africa is associated with the Saharan air layer. It's associated with suspended sand and dust in the middle troposphere that is kicked up over the deserts of the Sahara and then lofted to the middle troposphere and carried along from east to west by the wind associated with the African easterly jet and the broader scale circulation of the tropical Atlantic Ocean. The dust outbreaks tend to trail cyclonic disturbances. We've got one kind of very disorganized one here. We have Dorian here. The dust is typically found behind these features. Recall in our last lecture that we said that our cyclonic disturbances, African easterly waves in that case, grow at the expense of the jet. And so behind the jet, or behind the disturbance, it's stronger, where you have a jet that is stronger, that is. And so as we'll discuss in a few moments, a stronger jet leads to a greater potential for kicking up sand and dust from the underlying surface. And that's why we have these dust outbreaks associated with the Saharan air layer, typically having their greatest dustiness behind our cyclonic disturbances. And I'm just annotate in those clouds there. So let's discuss a little bit about how this Saharan air layer actually forms and what its characteristics are. So we've got this stock footage here of the Saharan desert, and we have the intense summer sun depicted here in the upper left portion of the diagram. So there's going to be shortwave radiation that this sun directs down toward the ground, given by these yellow squiggly lines here, and it's going to hit the sand. In a previous video, we talked about sand being a very effective absorber and conductor of the heat. So this solar radiation is going to heat up the sand to very high temperatures, certainly not anything you'd want to step foot on. Because it's absorbing all of that heat and has a very high conductibility, it's going to then try to conduct that heat back to the air that resides just above. And this manifests in the form of a surface sensible heat flux. The sand is hotter than the air that lies just above it, and so you're going to get a surface sensible heating that is directed upward. The sand is going to try to make the air warmer than what it was before then. So this triggers the formation of a super adiabatic or absolutely unstable lapse rate here right at the surface. Touching the surface, you're going to heat it up very strongly, so an air parcel is going to be able to rise on its own because it is absolutely unstable. And so it's going to continue to rise until it reaches to some level of neutral buoyancy. Early in the day, that's going to be very close to the ground, but as you go over the course of the day and have this intense heating, these vertical motions, the upward motions and then the corresponding downward motions away from them, are going to reach to greater and greater elevations. In particular, over the Sahara Desert, they typically reach 3 to 5 kilometers, somewhere between 7 and 500 hectopascals during the course of the afternoon hours during the summertime months. And so you get this very deep layer over which air is ascending because of the very strong heating of the sand. And in the midst of this layer, you're seeing the air mixing as it goes up and then ultimately comes back down away from that region of ascent. So it's going to try to make all of the properties of the air, in particular the potential temperature, the water vapor mixing ratio, but also the momentum, which is directly related to the wind speed, uniform over this vertical layer. And on a sounding, that manifests as this type of inverted V structure, where the temperature profile follows along a dry adiabat and the dew point profile follows along a mixing ratio line, and the wind speed often becomes relatively homogeneous over that deep vertical layer as well. So with the African easterly jet, it's going to try to bring that higher wind speed closer down toward the surface. And so if we take a look at a sounding here, let's focus on this solid black line that we see here for dew point, and then this one here for temperature. Ignoring what's happening right at the surface, where perhaps this is taken just after sunset, and so you're seeing a little bit of cooling right there at the surface. Note how from just above there all the way up to 500 hectopascals in this case, you have a lapse rate for the temperature that very closely approximates that of a dry adiabat. And then for the dew point trace, it's close but not quite resembling that of a mixing ratio line, again to about 500 hectopascals. So we're looking at something that's over 400 hectopascals deep from the surface, which is here around 925, 950 hectopascals, up to 500 hectopascals. So over the Sahara Desert, recall from our previous lecture that we have that heating-driven anticyclone in the middle troposphere. To the south of that, you have the easterly winds associated with the African easterly jet, until right at the surface you get the westerlies associated with the West African monsoon. So over much of this layer from the surface to 500 hectopascals, you have easterly flow trying to direct this air mass from Africa toward the Atlantic Ocean. And so once it reaches to the Atlantic Ocean, it's relatively cold there off of the coast of Africa, on the order of 25, 26 degrees Celsius, with the cold ocean current that comes from the north, along the coast of Europe toward North Africa. And so this air, you've got relatively warm air over Africa and relatively cold air over the Atlantic Ocean. So the potential temperature of the air, which we know should increase as you go upward at any given location, is higher near the surface over Africa than it is over the ocean. And so if it wants to keep that value of potential temperature, that air coming from Africa is going to rise to a higher altitude as it goes over that cold dome over the eastern tropical Atlantic Ocean. And so this mixed layer with a nearly dry adiabatic lapse rate and nearly mixing ratio line paralleling dew point becomes found at a higher elevation over the water, which is given by the dot dashed line here on the sounding. The base of that inversion is roughly around 850 hectopascals in this case, and note how it also doesn't extend to quite as high of an altitude, only about 600 hectopascals or just above. Whereas below that, you have the air mass associated with the eastern tropical Atlantic Ocean, with a relatively cool surface temperature of about 27 degrees Celsius and relatively moist surface temperature as well. So we get a structure that looks a lot like what we saw with the trade wind inversion, with a subsidence layer above an inversion separating that from the ocean-influenced air mass that resides beneath. So as a result, as this Saharan air layer is advected from Africa toward the Atlantic Ocean and ascends, it becomes an elevated mixed layer. It is a deep mixed layer over Africa, but one that's rooted at the surface. Whereas over the Atlantic Ocean, it becomes an elevated mixed layer, again with a potential temperature that's roughly constant and mixing ratio that's roughly constant over the depth of that vertical layer. So let's come back to this diagram that we had put together a couple of slides ago. We want to ask now, why is the Saharan air layer a dusty layer? We showed that it is dustier behind cyclonic disturbances. How do we actually get the dust there? We've kind of hinted at it over the course of some of this video here. Well, let's take a look at it in a little bit more formal of a context. So this 3 to 5 kilometer deep mixed layer that forms here in response to that strong surface heating reaches up to African easterly jet level. So let's add in the African easterly jet here, just depicting from right to left, assuming that it's an easterly jet in this particular case. So we noted on this diagram before that not only does it this mixing try to make uniform the potential temperature and the water vapor mixing ratio, but it also tries to do that for momentum, which is directly related to wind speed. So if you have higher wind speed here associated with the African easterly jet, this upward directed branch driven by strong heating, and then the downward directed branch that is not depicted here in the interest of a clear diagram is going to try to take some of this faster easterly wind associated with the African easterly jet and bring them down toward the surface in the form of wind gusts. We see this over land in any number of different circumstances. The gusts tend to be more prevalent during the daytime hours as opposed to during the night, and it's because of that localized heating of the surface that creates these localized forms of turbulence that reach up into the atmosphere and try to bring down some of the higher wind that is found there closer to the surface. So some of these gusts that are brought down toward the surface with these smaller blue vectors that are depicted at lower altitudes just above the sand kick up some of the sand and dust from the surface. This little fuzzy cloud bubble that is depicted here. And then these ascending branches of the heating-driven circulations loft that up into the mid-levels, and then the flow associated with the African easterly jet carries that along from east to west, including out over to the Atlantic Ocean, like so. So let's take a look at some characteristics of the Saharan air layer before we wrap up. Here on the diagram at left, we have the top and bottom pressure of the Saharan air layer over the Atlantic Ocean. Where is the bottom located in terms of its pressure? Where is the top located in terms of its pressure? So the bottom is the solid contours here. We see 900, 850, 800, 750, 700 hectopascals. So in general, as you go from the coast of Africa, which is here on the far right side of the diagram, to the west, the bottom of the Saharan air layer becomes found at a higher and higher altitude. Whereas for the top of the Saharan air layer, which is the dashed contours that we see here, we have 575, 550, 525, and 500. So too does the top of the Saharan air layer become found at a higher altitude. But note that the difference in contour values on the bottom is 50 hectopascals, whereas that at the top is only 25 hectopascals. So concurrently, if we look at the thickness, the pressure at the bottom of the layer minus the pressure at the top of the layer, we see that it has greatest thickness, 350 hectopascals just off of the coast of Africa, and then becomes smaller, down to 150 hectopascals by the time you reach 37 to 40 degrees west longitude, still over the tropical Atlantic Ocean. So it has its greatest thickness and is found closest to the surface near to the coast of Africa, and then becomes found at higher elevations, but with smaller thickness as you move from east to west from the coast of Africa toward the central tropical Atlantic Ocean. One of the discussion prompts associated with this lecture material asks you to use that lapse rate tendency equation that we introduced with the trade wind inversion to try to understand what factors could cause the base of that Saharan air layer to be found at progressively higher and higher altitudes, and why the depth of the layer may become smaller as you go to those higher altitudes. So I encourage you to take a look through that and let me know if you have any questions as you work through that. Finally, we can also take a look back at some of the characteristics of the Saharan air layer, which we first introduced in our tropical climatology lecture, relying on the results of Jason Dunyan's work from 2011. Here at left, we have relative humidity profiles, and each one of these red lines is from a different year's worth of data, 1995 through 2002. They all overlap pretty close to one another, and so we're not particularly interested in looking at differences between those years. The solid black line is the Jordan 1958 sounding, which is said to be a tropical mean or average sounding. And in particular, note the dryness, especially above 900 hectopascals and then from 700 hectopascals on upward. You're looking at relative humidity on the order of 30%, give or take 5 to 10% on either side of that, from 700 hectopascals all the way up to the tropopause and beyond. So you're looking at very dry mid-level air as you are mixing that very hot, very dry air from the surface upward into the troposphere and mixing it downward toward the lower troposphere as well. We've noted that this feature is also concurrent with the African easterly jet, and so we introduced this wind speed and direction profile information before. The wind speed for the Saharan air layer sounding, which is this red line that we have here, is maximized between 900 and 600 hectopascals at 6 to 8 meters per second. Noting again that these soundings aren't off the coast of Africa, but they're way out near Puerto Rico, the Bahamas, Jamaica, and Florida, so well away from the African easterly jet itself specifically. But nevertheless, the wind direction here, all the way up from the surface to 300 hectopascals, is 90 degrees. It's from the east toward the west. So the Saharan air layer is typically a very dry layer with very strong winds, comparatively speaking, out of the east in the middle troposphere, roughly 900 to 600, perhaps even 500 hectopascals here. So summarizing our discussion about the Saharan air layer, we discussed how it results from strong surface sensible heating over the Sahara Desert that promotes that deep vertical mixing. Very large potential temperature, very low water vapor mixing ratio, and bringing faster winds from the African easterly jet level down toward the surface in the form of wind gusts. And it's those gusts associated with mixing to the level of the African easterly jet that kicks up the sand and dusts. We said that that is strongest between easterly waves because, again, the easterly waves grow at the expense of the jet. They weaken the jet to make themselves stronger. So the jet is stronger between waves, and thus the gusts associated with the jet that reach down to the surface are also stronger. The heating is also stronger behind waves as well because you don't have the cloud cover and precipitation associated with the waves to be able to block the strong heating of the Sahara Desert. Finally, that Saharan air layer becomes elevated as it passes from Africa to the colder eastern North Atlantic Ocean. And as it passes over the North Atlantic Ocean and as water temperatures warm from 25 to 26 Celsius near the coast of Africa to 28, 29 Celsius as you move further to the west, the Saharan air layer becomes further elevated and becomes shallower in nature. So that wraps up our dialogue about tropical jets and disturbances. We move on from here into tropical cyclone climatology, finally flipping the switch as we've seen a lot going around TikTok, and don't ask me to describe how I know that or why I know that, but we flip the switch over to tropical cyclone climatology as we move into our next module. So until then, thanks for tuning in.